Hi, this is lesson 1.1, standard form. Let's get started. We're going to be graphing quadratic functions. The first key issue we're going to talk about with quadratic functions is what's a function? Okay, so I'd like to show you a picture of what is a function and what is not a function and see if we can figure that out from looking at the picture. So this over here on the right-hand side, this is a function. And this over here on the left-hand side is not a function. Okay, so I don't know if you notice anything different. Some things you might notice are these are individual points, and this is actually a curve with some points on the curve. So if I look here, it looks like these points all here are all by themselves. And if I look down to the x-axis, this point right here is negative 311, and this is negative 2, 5, and this is negative 1, 3. Okay. What's different about over here? Well, let's see, what jumps out at me right away is this thing right here. I have a point that is 0, 1, and a point that is 0, negative 2. And that's actually part of why this is not a function. That's why this is not a function. So let's go look at the definition of a function. A function is a relation in which each input has only one output. And this is one of those times where the first thing that pops into my head is, well, what's a relation? Okay, so then let's talk about what a relation is. A relation is a set of inputs and outputs, often written as ordered pairs. So it's what we think of as when we say an x value, which is my input, and a y value, which is my output. All right, so that's a relation. Any x ordered pair is a relation. There's an input, there's an output. A special relation is a function. A function is a relation in which each input has only one output. So if we look at these 2 points right here, this one is the point 0, negative 2. Oh, my 0 doesn't look very good. And this is the function 0, the point, 0, 1. So in this relation, I put in a 0 and I get out of negative 2. And I put in a 0 and I get out of 1. And that means that it's not a function. I know at some point in the lower grades, they probably talked to you about a function as thinking of it as a machine. So if you thought of this as a candy machine, you went over and you put in a quarter and you got out a Hershey's bar. So that's your negative 2. And then you put in a quarter and you got out a different candy bar. So maybe you got out a Zagnut bar. So that's not a function because every time I put in that quarter, I should get out the same candy bar. I shouldn't be getting out a different candy bar each time. So when I pull that lever to get the candy, I want to make sure I get the same candy. So this doesn't work. It's not a function. So your input, for every input that you put in, you have to get out the same output. One way to see it is this is a relation. And my question is this a function? All right, so these are my inputs over here, and these are my outputs over here. So remember, to be a function, if I put in a value, I have to get out the same number every time. So here, if I put in a 0, I get out a negative 2 and a 1. That's not a function because there's confusion going on there. So the way I always remember it is if I'm ever looking at something like this, a mapping diagram, if you get something that looks like that, we input something and got 2 other values coming out, so it looks like a sideways V, that's not a function because you've got 2 different values once I put that 0 in. If I look here, a 1 gets me a 2. That's nice. That would be part of a function. A 2 gets me a 1. And a 3 gets me a 4. So the only reason this set of data is not a function is just because of the top one right there. Okay, so let's look at the next one. Key issue number 2. What is a quadratic function? Look at the graphs and then look at the equations. And then we're going to decide what makes something a quadratic function. So on this side over here on the left, these are not quadratic. So this one tells you right here, it says it's a linear equation. And this is the equation of the line. Y is equal to 3.5 minus 0.5x. So that's a line with a negative slope. This one down here, it is g of x is equal to x cubed. That's a cubic. And over here, we have this curve going on here, and it's f of x is equal to 0.5 raised to the x power. Okay, that's an exponential equation. And this is our quadratic over here. So we can see the difference from pictures. So I can tell that the graph is a quadratic because it is. So what makes this a quadratic over here? Well, its shape. So it is a, and the name for it, I'm just going to type it here, is a parabola. So quadratics are all in the shape of a parabola. I can tell that the equation represents a quadratic because, right, so this is a linear equation on the left-hand side here, and it's linear because it is x raised to the first power. This is x raised to the third power. This is a number raised to the x. You can see that it is a number raised to the x. And over here, we have x to the second power. Quadratics are all x to the second power. So I can tell that the equation represents a quadratic because x is raised to the second power. And you can also just write x squared on the line. Okay, so you now should be able to look at a graph and tell that that's a quadratic. You should be able to look at an equation when you see x squared and be able to tell that's a quadratic equation from the equation. All right, so key issue number 3. What are the key components of a quadratic equation? A quadratic function is in the form of f of x is equal to ax squared, where a is a number, plus bx plus c. A cannot be 0. Because if I multiply 0 times x squared, then the x squared value goes away, and I just get a linear equation. So a is not 0. Okay, this function makes a shape called a parabola. So that's one of the key components, or one of the descriptions for the graph. The main components of a parabola are its axis of symmetry and its vertex. Okay, axis of symmetry is just what it sounds like. An axis is a straight line. So the axis of symmetry is the line that goes right through the vertex here. Okay, so a vertex is just a point. It's an x value and a y value. And in this case, our x value is, see, we're over 2 and up 0. So, I'm sorry, over 2 and down 1, I apologize. So that's our vertex. We can read it right off the graph there. What's the value, or what is the equation for the axis of symmetry? So we just found our vertex. I'm just going to write it over here to the side. So vertex is the point 2, negative 1. The axis of symmetry is a vertical line. All vertical lines are in the form of x is equal to. So you have to say to yourself, what's x equal to? Well, it passes right through this point right here. So that means that every single x value on that line is equal to 2. So the axis of symmetry is the x value of your vertex. Okay, the y-intercept. Y-intercept is here, and it's in this form, where the first value is a 0. Why? Because you're going over 0 in the x direction, and the next value is c. Now I'll talk about where that c comes from in just a minute. The x-intercepts are here. So where does this graph cross the x-axis? It crosses right here and right here. And x-intercepts are in this form, where you write them as x comma 0. So they're a point. The minimum value for this graph is right here. It's also its vertex. So you find the minimum value by finding the vertex. And let's talk about the y-intercept. Notice it says 0c. Well, where do we get that from? We get that from up here. So we said that a quadratic function is in the form of ax squared plus bx plus c. So why is the y-intercept c? Because the y-intercept is where the x value is 0. And if I do this and I say f of 0 is equal to a times 0 squared plus b times 0 plus c, well, that goes away because that's 0. That goes away because that's 0. So if I put a 0 into any equation that's in standard form, what I get out is c. So I can always read my y-intercept right from the equation. I think one of the toughest issues to understand with a quadratic equation or within any equation, what's the domain and the range for the quadratic function? So you need to remember the definition of a domain. The definition of a function, the domain of a function is a set of all real values of x that give real values for y. So the way I like to think of domain is all the possible x values. What's the range of a function is a set of all real values of y that you can get by plugging real numbers into x. So what's range? All the possible y values. Okay, so what does that look like on the graph? I'm going to show you two ways of thinking about it, and maybe one of them will stick with you. The first is if we think of to determine domain, or all possible x values, the quadratic function, look left and right on your graph. So if I come over here and I'm looking at this graph right here, and I'm looking at all of the possible x values, well, this graph is going to continue going that way, and it's going to continue going that way forever, and it's going to continue going that way forever. Okay, so then what are my possible x values? Well, you can see as you go along here, this has an x value here, this has an x value here. If I keep going up on my graph, that value's there, that value's there. This arrow goes on forever. So in the x negative direction, it goes on forever. And in the x positive direction, it goes on forever. So we say that the domain is all real numbers, or we can write it as, and it's really sort of hard to read down there, it is x is greater than negative infinity and x is less than positive infinity. And that's one way to think about it, or one way to write it. How do we figure out what the range is? The range is all my possible y values. So since the minimum y value of the function is 0, so if I look here, this is the lowest that graph comes. It comes right here. So the minimum value of the function is 0. So the graph continues to go upward like that. Then it means that my range are all of those values that are greater than 0. So we say range is y values greater than 0. So remember, domain is x, range is y. Okay, one of the ways I like to think of it, and this is sort of stuck in my head, so let's try this. What's domain and range of a function? Imagine that you're taking the arrowhead. So imagine that this is my, parabola. Okay, and this arrowhead's on either end. And imagine that you take the two arrowheads. So he's taking the arrowheads and he's squishing them towards the x-axis. Okay, so he just pulled them down. And what do they look like now? It looks like a number line. So how many numbers on the number line? All of them. So it's all real numbers. So the domain is all real numbers. And you found that by just taking the two arrowheads and squishing it down towards the x-axis. So you pulled them down here and pulled it down here, and it forms a straight line. Okay, range. What's the range of the quadratic function? Again, imagine you're taking the two arrowheads. So you're always focusing on those arrowheads. So here's my parabola, and this is one that's going up. Okay, here's my arrowheads. Imagine that I take those two arrowheads and see how his hands are up in the air like that? If he claps them together. Well, what happens when he claps them together? I get a straight line going up. So what's my range? My range is all the numbers bigger than his chin. So anything going up that way. If the curve went down like this, then it would be, I'm going to start right here at her back, and any numbers that would be less than that spot. So any y values, it'll be less than that spot. So the range is determined by the minimum and the maximum